Welcome to our discussion on proportionality. This is actually just a kind of more specialized definition of ratios, right? We've already been dealing with this stuff. We already know how ratios work. We've already seen odds. We've seen this thing of A to B. And when we talk about things in this context, we know that if A is somehow related to B, right? A to B, then we can set it up as a fraction as A over B. And then we know that if we have a fraction A over B, we can multiply top and bottom by n, right, and get NA over NB, which means we now have this similar ratio of NA to NB. For instance, if something was 3 to 1, right, we would put 3 over 1. But we could multiply top and bottom by, let's say, 2, and then we would get 6 over 2 or 6 to 2, but 6 to 2 is the same thing as 3 to 1, right? We normally, when we talk about ratios, we reduce them. Instead of 6 to 2, we reduce it down to 3 to 1, and so on and so forth. So you've already seen most of this before. All we're doing now is letting you know that when we talk about these ratios, we're really also talking about two quantities that are directly proportional, and they can actually be written in this way here with y equals kx. There's some sort of multiple between the two. For instance, if these things are 3 to 1, then that means you could take whatever amount of this quantity you have, multiply it by 3, and that's how much you have there, right? See, if you have 2, let's say, pounds, multiply it by 3, now all of a sudden you have 6 pounds. So you can think of y as being in the place of 6, and this number here, right, is your x, and then your constant of multiplicity, or constant of proportionality, in this case, is going to be 3, because you have to do 2 times 3 equals 6. And basically, we then end up seeing that these simple ratios are really nothing more than, right? So if we have 3 to 1, that's really the same thing as saying y is going to equal 3x, because for every number we put in for x, right? Remember, these are going to be our x's and these are going to be my y's. Then y is 3 times as much. All right, that's easy when it's a 3 and a 1. What happens if we have, let's say, 4 to 3? All right, so this is my y, this is my x. You could still figure out that constant of proportionality very simply and easily by using this formula. We know y equals some constant k times x. We don't know what that constant is, but we can solve for it. Plug in everything we know. 4 equals k, and then x is 3. And if we want to solve for k, we divide both sides by 3, and we get 4/3 equals k. So now we can say that this ratio, right, 4 to 3, is the same thing as y equals 4/3 x. And double check it. Plug in a 3 for x, and you see that 3 times 4/3 gives you 4, and it spits out an answer of 4 for y. Okay, so all we're doing with this chapter is we're introducing ourselves to this idea of proportionality. And we've already seen direct proportionality, and then we're also going to talk about indirect proportionality. So here's a simple example looking at converting between two different currencies, right? If you're going to travel overseas to Europe and you're going to buy some euros and you had US dollars, well, if you were lucky, you would get this kind of exchange rate. That right now the exchange rate is 4 to 5, meaning that 0.8 of a euro equals $1. So basically the euro is stronger than the dollar, right? Because if you give them $1, you get less than €1 back. So that's what it means if you ever see on the news they're talking about, the euro is getting stronger, or the pound is getting stronger, or the US dollar is getting stronger. It just means that our ratio is getting better. Right now, the dollar is weak according to this example, because you basically have to spend more dollars to get euros, right? So 1 euro is going to equal more than $1, right? So that means it's weak. But you can see this ratio of 0.8 to 1 holds no matter what you multiply it by. If you multiply it by 5, and there's your 4 to 5. There's this ratio, because that's normally what we do with ratios, is we list them with two whole numbers and the smallest possible pair, right? So instead of 8 to 10, we would say 4 to 5, and we would say 4 to 5 instead of 2 to 2.5, because 2.5 isn't a whole number, right? And that just kind of 2 to 2.5 is just like weird. The only time we ever kind of do ratios where one of the numbers is not a whole number is when we have this idea of letting one of them equal 1, because 0.8 to 1, we can kind of wrap our heads around that, but 2 to 2.5 isn't as easy to understand. All right, so we could do the math, we could figure out the rest of these. Not going to waste time talking about that, right? It's still just basic ratios. This constant of proportionality, big fancy word that just says that's that number k that you can solve for, and we call it a scaling factor. It's basically the number that if we multiply one side of the ratio by, it's going to give us the other side. And normally we set it up with y being the number on the left and x being the number on the right. But there is, no reason why you can't switch places. So if you're doing homework or you come across something on a quiz or test, just make sure you pay attention to the details, and somewhere in there they should tell you which one is x and which one is y. All right, well, when we have the ratio reduced down to something to 1, right? So 0.8 to 1, that makes it really easy to figure out our constant of proportionality, because if x is 1 and y has to be 0.8, then we obviously have to multiply by 0.8, and that tells us that in this case, k is 0.8. So that's the other reason why we will reduce ratios down to something to 1, because then that gives us the constant proportionality. Now, if we went the other direction, right, this was where the dollar was 1 and the euro was 0.8, but maybe we want to make the euro 1 and the dollar something else. So in this case, if we divide both sides by 4, we're going to get 1 to 1.25, and you can see that 1.25 ends up being the constant of proportionality if we're going in the other direction, right? We would still have the same formula of y equals something times x, only now the something would be 1.25. But then, that's technically a completely different function, right? It's a completely different line, and it has a completely different constant proportionality, because when we do the 1.25, that means we're plugging in euros and getting our answer in dollars, whereas when we have the 0.8, we're plugging in dollars and getting euros. So you can see that these two equations, right, equation 1 and equation 2, are really just y equals kx, but instead of using y's and x's, we used E and D for euro and dollars, right? Euro and dollars. And so it makes a little bit more sense. Instead of just these arbitrary X's and Y's, now these variables have meaning. And now when we look at these, we know, oh, well, the dollar is the input, euro is the output. Euro is the input, dollar is the output. So if I've got dollars and I want to figure out how many euros I'm going to get back, I would use equation 1. I'd plug in the, I'm going to give them $20, and then I'm going to multiply it by 0.18, and they're going to give me back 16 euros. And then I'm done with my trip and I'm coming back home and I want to trade my euros in for dollars, and I want to know how many dollars I'm going to get back, and I've got 40 euros left in my pocket. Obviously, I must have got some more euros along the line because I started with 16, right? But I got some more euros and now I have 40. If I give them 40 euros and I multiply that by 1.25, I'm now going to have 50 US dollars when I get on the plane to go back to the United States. All right. So that's why it's nice to use E's and D's instead of X's and Y's. It just makes more sense to use variables that are related to that particular topic rather than just these arbitrary X's and Y's. All right, so here's a simple example of how we could do it in Excel. I don't particularly like the way they did this, only because there's nothing wrong with it. It's just kind of silly. Why would you define this cell here as A3 times E2? Why not just define it as E2 times whatever the current exchange rate is? And I get that, that's what this is, but if that's the case, then why bother with this form? I don't know. It just seems like there's a lot of extra junk going on in this that you could, I think you could clean this up and do a much more efficient way, let's say, of doing that kind of work. Now, if we filled in a table with some values, Obviously that, constant proportionality up here, 0.8, so everything's being multiplied by 0.8, and then if we graphed all of these points on a graph, we would see that we would get a nice straight line, which makes sense because if we look at E equals 0.8d, isn't that y equals mx plus b, right? That's a y equals mx plus b. That's a straight line where your m, your slope, is 0.8, and your b, your intercept, is 0, right? Because this is really just y equals mx. There's no b on the end. And so that's why it starts at 0, 0, because that makes sense, right? If you have $0, you're going to get €0 back. It wouldn't make sense to have it any other way for the origin, right? When you have 0 input, you should have 0 output for this type of thing. And then you just get a straight line with a slope of 0.8. So here it is again. The blue line represents that what we call direct proportionality. Anytime we have direct proportionality, we get this y equals kx kind of idea. So as your x values go up, your y values go up by some proportional amount, right? So 0.8, 1.25, right? Any constant will do. But we can also have inverse proportionality. And inverse proportionality means as one thing goes up, the other thing goes down. And you can see there's a big difference on how these things work, right? Instead of y equals k times x, it's y equals k divided by x. And so now can you see that it makes sense as x gets bigger? Remember, k is a constant. We just don't know what it is. It changes from case to case, right? If we're doing euros and dollars, it's 0.8. If we're doing dollars and euros, it's 1.25. If we're doing something else, it's something else. But of course, those examples would be over here because those are direct proportionality. But if we had an inverse proportionality, some k is just some constant. And as x gets bigger and bigger, we're dividing by a bigger and bigger number, which means we're getting a smaller and smaller answer. And if we graph that, that's going to be the red line. And in the case of the red line, we did it with k equals 2. So every time x gets bigger, you're cutting 2, right, by bigger and bigger numbers. You can see that when x is really small, when it's a fraction, when you divide by a fraction, so like let's think of x being as 1/10. If you divide by 1/10, you're really multiplying by the reciprocal, 10 over 1. So that's why you get a big number. And then when you divide by 1/100th, you're really multiplying by 100 over 1. And so this thing is going to shoot off up here to infinity as x gets closer and closer to 0. Can x ever equal 0, guys, in this case? And hopefully you're all saying no. That's correct, because you can never divide by 0, right? And then also, as x gets bigger, we're dividing by bigger and bigger numbers, so we're getting smaller and smaller fractions, and this thing comes down and gets what we call asymptotically. The asymptote, the horizontal asymptote, is the x-axis. This thing's going to hug up right next to the x-axis. Will it ever equal 0? And again, no, because no matter how big x gets, it's always going to be something divided by that. And this is going to be a really, really small fraction, but it's never actually going to equal 0. So this thing gets asymptotically close to the y-axis and asymptotically close to the x-axis. Basically, it hugs up next to both of them. And that's what happens when you're inversely proportional. But, it's basically the difference between y equals kx and y equals k divided by x. And you might be asking yourself, well, how do I know when to use one or the other? Well, most questions will say something is directly proportional to something, or something is inversely proportional to something, and then you know right off the bat which formula to use. If they don't actually come out and use those words, then there's going to be some sort of context of the question that's going to give it away. They'll give you two examples that x is something and the y is something, and then there's another example with a different x and a different y, and when you solve for k, you see that, oh, okay, well, as x gets bigger, y gets bigger, so this was a direct. But they'll give you another example where x gets bigger and y gets smaller. So for instance, let's say they gave you two pairs of numbers and they said, find find a formula, find either direct or indirect that fits these numbers. And they don't tell you whether it's indirect or direct. They just say, okay, when, here's my x and my y. When x is 3, let's say y is 10. And when x is, let's say, 6, y is 20. And you go, well, x got bigger, y got bigger, so this has to be a direct proportionality. And now I can plug in either pair, doesn't matter which, right? So I can go 10 equals k times 3, divide by 3, and k equals 10 thirds, or 3 1/3, or 3.333, whichever way you want to do it. And they go, okay, well, how about this scenario? Here's my x, here's my y. When x is 3, y is 10, but when x is 6, y is, let's say, 5. And you go, hey, it got smaller, right? X got bigger, y got smaller. So now I know it has to be this version. It has to be y equals k over x. And now let's plug in and see what we get. So we'll take the first one and plug in 10 equals k over, right? This is y, this is 3. Multiply both sides by 3 and we get 30 equals k. And so now we know it's y equals 30 over x. And if we plug in the second set of numbers, plug in my 6, right? 30 divided by 6 is 5, and it works. So now we found the function for that one. So don't panic about trying to figure out when to use which. It's going to be very obvious with the context of the question. Either they're going to specifically tell you this thing varies proportionally with this thing varies inversely with that, or they're going to give you 2 points and say fit one of these functions to it. And if y gets bigger as x gets bigger, then we know it has to be a direct proportionality. And if y gets smaller as x gets bigger, we know it has to be inverse proportionality. And in either case, they're pretty easy to solve. All right, that's it for this chapter.